All right, let's talk about resonance. Whether you're at Module 6 already or not, um, this is one of the most important topics in any organic chemistry class. It will come up over and over and over and over and over again because it has this great explanatory power. All right, so I'm going to start with the question of what is resonance. If you hear the term resonance, what does it mean? So resonance is a situation. Oops, where one Lewis structure is not sufficient to describe a molecule. So Lewis structures, they're these really simple things that we draw to represent molecules, but they're not perfect. Um, Lewis structures aren't reality. They're just a pretty decent representation of most molecules. So for a simple molecule like, I don't know, methanol, CH3OH, I could draw this Lewis structure for methanol, and it's a pretty decent representation, and it captures most of the things you would want to know. Now, sometimes you need to know the shape, and so sometimes just drawing the Lewis structure but not drawing it in the right shape wouldn't be a good enough description. So sometimes for a molecule like methanol, I might want to draw it in the correct shape. And so in a case of a simple molecule like methanol, one of those representations might be perfect for most descriptions, might be perfect for most uses. All right. So here is a case where the Lewis structure works fine. Simple molecules like methanol. When you have resonance, that's a situation where one Lewis structure just doesn't do the job. So a classic example of that would be the molecule ozone. So this is ozone. It's the thing up there in the ozone layer. That protects us from UV rays. That molecule ozone is a situation where one Lewis structure doesn't work very well. And the reason is, if I draw this Lewis structure for ozone, it makes me think that, okay, ozone molecules have a single bond and a double bond. They have a positive oxygen in the middle, a negative oxygen on one side, and a neutral oxygen on the other side. The problem is when you look at the actual structure of ozone, that's not what you see. In the actual structure of ozone, both bonds are equivalent. And both oxygens on the outside are negative. So if that's the case, this one structure is essentially lying to us. Right? This one structure can't describe the molecule because it makes it look like we have two different kinds of bonds in the molecule. It makes it look like one oxygen should be way more negative and the other one shouldn't be. So this is a Lewis structure failure. So we need a better description of molecules like ozone, and it turns out lots of organic molecules too. Lots of organic molecules are going to exhibit resonance. So one Lewis structure is not good enough to describe the molecule. So how do we deal with this? We deal with it by drawing a second resonance structure. We deal with it by drawing multiple structures. So the solution for ozone, what that means is we draw both the original one that I drew and another one and what we say is neither one of these on its own is a good representation of the molecule. The actual molecule itself is going to be what we call a hybrid of the two. All right. So in the actual structure of this, what we have is something like 1.5 bonds on each side. And something like half a negative formal charge on each of the outer oxygens. And what we say is this extra bond here, it seems like there could be a double bond on both sides. This extra bond is what we call a delocalized pi bond. If you haven't done Module 5 yet, you might not know what pi bond is yet, but we'll get there. But it's a bond that's shared not just between two atoms. It's a pair of electrons not shared just between two atoms, but among more than two atoms. So this is shared among more than two atoms. So the question is, what do we do for lone pairs on these two outside oxygens? And we don't have a good way to represent them, because is it, should we put 5 electrons on each one? That's not a great representation. So the thing is, this representation that I drew at the bottom is one that we're not generally going to draw. Generally, what we do is we draw the resonance structures themselves. Okay? this representation down at the bottom is something where I'm just drawing to give you the concept that there's an extra bond that's kind of spread among those three atoms. But we don't tend to draw this kind of representation. Instead, what we draw are the resonance structures. So yeah. So the question is, do you mean we as in this level? When I say we, I mean in this class and in most courses. Um, this kind of representation is used to introduce the idea of resonance. And I want you to get this idea of the resonance hybrid, that the actual structure is a hybrid of the two resonance structures, or sometimes three resonance structures, or sometimes four or five. That it's a hybrid of those, but we won't ever draw these again, this kind of representation at the bottom. We tend to stick with Lewis structures and just draw the multiple resonance structures when we need them to explain something. Because Lewis structures are much more fixed. They follow a fixed set of rules. We know where the lone pairs go. But we need to be able to interpret when we draw resonance structures what that actually means. Okay? So, first thing I would say, I want to point out what resonance is not. And what resonance is not, it's not an equilibrium between the two structures. It's not a situation where the molecule goes back and forth between being one structure and then the other structure. All right? So this is not an equilibrium between the two. The molecule does not go back and forth. From one to the other. So this term hybrid, most of you have heard in biology before. A hybrid is usually a cross between two species. When you make a hybrid, like what's an example of a hybrid? A Toyota Camry, or like you mean a Prius? Yeah, a Prius is a hybrid. Okay, well, why is a Prius called a hybrid? It combines an electric and a gasoline. Now, does a Prius go back and forth between being like is 1 second the Prius a Chevy Volt, and then the next second, or like a Tesla, like an all-electric car, and then the next second it's a regular Toyota Camry that's an all-gas engine car? Does the engine actually swap out second by second? No. What's another example of a hybrid? A liger, cross between a lion and a tiger. Is a liger a lion 1 second, and then a tiger the next second, and then a lion, and then a tiger? No. Same thing with a mule. Mule's a cross between a horse and a donkey. It doesn't go back and forth between being a horse and being a donkey and a horse and a donkey. It is a thing that is somewhere in between a horse and a donkey. So the idea with a hybrid is it's not something that goes back and forth between two states. It's something that is a thing. It exists in one state in between the other two things. Okay? So resonance is not a situation where it's going back and forth from one structure to the other. It is never the resonance structure on the left, and it is never the resonance structure on the right. It is always somewhere between the two. Okay, that's an important concept. Yeah. So the question is, why can't we just say this representation I drew at the bottom is the best way to represent it? Again, when we start drawing mechanisms for reactions, we need to have specific places for the lone pairs to be drawn, and this kind of representation at the bottom is problematic for that reason, and so we tend not to draw them that way. So that is, we have decided, I guess the chemistry community has decided our best way to represent these is going to be to draw multiple resonance structures, but to say, okay, you need to recognize the actual structure as a hybrid of the two. It's not a perfect solution, but it's the one we've got. It's the way we've adapted Lewis structures to confront this problem of molecules that aren't well described by a single Lewis structure. So resonance is not going back and forth. It's existing as a hybrid. All right. So I brought up this term delocalized pi bond. So a localized pi bond, localized bonds are generally shared, pair of electrons shared between two atoms. And then a delocalized pi bond would be one pair of electrons shared among more than two. So the way this works in a molecule like ozone, pi bonding happens when p orbitals on neighboring atoms line up parallel to each other. So pi bonding, parallel p orbitals. You'll learn about it in Module 5 if you haven't done it yet. But pi bonding comes from overlapping parallel p orbitals. In a typical localized pi bond, you have two atoms that have their p orbitals overlap, and they make that pi bond. So normally, you'd have just two atoms with their p orbitals overlapping. In a delocalized pi bond, you just have more than two. So it might be 3 or 4. In the case of ozone, it might look like this. You'd have your 3 oxygen atoms, and all 3 of them could have p orbitals lined up parallel to each other. And I didn't make them all overlap very well, but the idea is you have more than 2 atoms with parallel p orbitals. So I'm going to give you a visual for that, or a few visuals. So here is a view of the pi bond in ethylene. So ethylene is C2H4. So you can see my 2 carbons and my 4 hydrogens. The pi bond in ethylene looks kind of like a hamburger bun. Oh, and I'm going to have to close the window shades. I'll turn the lights back on in a minute. So the pi bond in ethylene is a localized pi bond. It's between these 2 carbon atoms. And it looks like a hamburger bun above and below them. That's a localized pi bond. Formaldehyde, CH2O, same idea. You've got the pi bond between the 2, between the carbon and the oxygen. Because there's a double bond between the carbon and the oxygen. pi bond looks like a hamburger bun, but it's a hamburger bun that's basically around those two atoms. Delocalized pi bonds can be found in things like the carbonate ion. So this is CO3 2 minus. So in CO3 2 minus, I've got 3 equivalent bonds between carbon and the 3 oxygen atoms. And the pi bond, notice, is spread out over all 4 atoms. So just to draw what the resonance structures look like for that. CO3 2 minus, we can draw 3 different resonance structures. Like this. So there's one pi bond that's spread over all 4 atoms, over the carbon and all 4 oxygens, and this is what it looks like to have one pi bond spread over those atoms. Benzene, C6H6, is another great example of resonance. So in benzene, we have 2 equivalent resonance structures. One that looks like this, and one that looks like this. And so what we have there are pi bonds that are delocalized around all 6 carbon atoms in that ring. And so what that looks like is really a big hamburger bun over all of them. Shrink it down and make it look more like a donut. Oh, it went away. It's really around all 6 carbon atoms. All right, so this is the difference between localized pi bonding, delocalized pi bonding. And the thing about Lewis structures is they're set up really well to describe localized bonding. Lewis structures, individual Lewis structures, do a good job when all your bonds are localized. But when you have delocalized pi bonding, a single Lewis structure just doesn't work. And that's why we need this resonance description. So any questions about what I mean by delocalized pi bonding? So the question is, can molecules with triple bonds have resonance? Definitely. So a molecule with triple bond can have resonance. Now the thing is, in a triple bond, there are 2 separate pi bonds, and so only one of them is going to be involved in the resonance system, and the other one will probably be a localized one. So generally, when there's a triple bond and there's delocalized pi bonding, only one of the pi bonds of the triple bond will be involved in it. But yes, that can definitely happen. All right. So we said when you have 2 resonance structures and they're equivalent, right, the actual structure is a hybrid of the 2. When I say equivalent resonance structures, what I mean is equally stable. So with ozone, those 2 resonance structures we drew were equally stable. And to judge stability, we would use the same 3 rules we've always used to judge stability. 1, octet rule. 2, minimizing formal charge. And 3, putting formal charge based on electronegativity. So to judge stability, It's still the same three rules in order of from most important to least. Still those same three rules. But when we look at two resonance structures and they are equally stable, the idea is the actual structure is going to be exactly halfway between the two. All right. So in the case of ozone, they were equally stable. I'll give another example. This is the acetate ion. These two resonance structures are equally stable. They both follow the octet rule. They both have one formal charge, and that it's a negative formal charge on oxygen in both. So these two are equally stable. Therefore, the actual structure will be exactly halfway between the two. The other examples I showed were also cases where the resonance structures were equally stable. So for carbonate, all three are equally stable. So the actual structure is an equal hybrid of the three. All three bonds would be equivalent. The delocalized pi bond is shared equally among all three oxygen atoms. With benzene, these two resonance structures are equally stable. So the actual structure is going to be, all the bonds in benzene are going to be completely equivalent. Okay, equal sharing. Where it gets a little trickier is when we have inequivalent resonance structures. So, for example, can anyone name that functional group? Just out of curiosity. This is an amide. It's an amide. Yeah. It looks like it should be. It's spelled like it should be amide, but we say amide for whatever reason. So this is an amide, and whenever you have an amide, you have the potential for resonance. Okay. We have these two resonance structures. So I want to compare the stability of the two. What's the first thing I look at? Octet rule. All right, the one on the left, carbon has 2, 4, 6, 8 electrons around it. Oxygen has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. All right, the one on the left follows the octet rule. The one on the right, oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. So the one on the right also follows the octet rule. All right, so I go to rule number 2. Rule number 2, minimize formal charge. Is there a difference there? Definitely. So this structure on the left This is going to be the more stable resonance structure. This one on the right is going to be less stable because it has non-zero formal charges. So what that means, the way to interpret that is to say, well, the hybrid structure, the actual structure of this molecule, is going to be somewhere between these two, but it's going to be closer to the one on the left. All right? So this is a case where the hybrid has two parents, and it resembles one parent more than the other. When people have a baby, they're, oh, looks so much like mom, looks so much like dad. This is a case where the hybrid resembles one a lot more than the other. So in this case, the actual structure is between the two, but closer to the one on the left. We don't have a good way to represent this. So this is another reason we don't draw these other representations. But if I were to try to draw my alternate representation here, what would I do? I'd say, well, there's going to be more double bondness between the carbon and the oxygen and less double bondness between the carbon and the nitrogen. So, I don't know, what would I do? Like put the dots closer together between the carbon and the oxygen, and then the dots a little farther apart between the carbon and the nitrogen? I don't know. So we don't have a great way to represent it, which is why we stick with drawing the two resonance structures, and you've got to learn to interpret what that means. What that means is there is some pi bonding between the carbon and the nitrogen, but it's not as effective as the pi bonding between the carbon and the oxygen. I wonder. So I built this molecule, and in my little program here, I built the molecule, and it does have a pi bond that is spread among the three atoms. But that pi bond is going to lie a little bit more between the carbon and the oxygen than between the carbon and the nitrogen. And that can be hard to see in this picture. I wonder. Yeah, it's hard to distinguish that, but there is a pi bond that is spread among the three atoms. Yep. So I was just asked to revisit this slide for a second. Oops. All right, questions so far? All right. So the next question is, how do I know when there's going to be resonance structures? Right? I've talked about how to interpret them, but how do I spot when there can be resonance structures? So here are the things to look for. All right. The most common one would be a lone pair on an atom neighboring a double bond or a triple bond. So a lone pair that lives next door to a pi bond. So for example, if I had this functional group, can anyone name that functional group? We'll keep working on them. It's not a ketone. It's close. It's an ester. Yep. So this is an ester. All right. This ester has 2 lone pairs on this oxygen over here, and those lone pairs are 1 atom away from a pi bond. So the fact that there are lone pairs right next door to that pi bond means resonance is a possibility. And I'm going to introduce to you something we call the curved arrow formalism. Something that is a very useful tool for us in organic chemistry. What we do is we take a pair of electrons and we draw an arrow to show it moving from one spot to another. Okay? So this lone pair can move to be shared with the carbon. Right? Pairs of electrons, they like to be shared. Why do pairs of electrons like to be shared? If you're a pair of electrons, what do you like most in the universe? Positive stuff. So, you have your choice to be on one nucleus or shared by 2 nuclei. You're going to take shared by 2 every time. All right? So, I have this lone pair and it says, hey, oxygen, maybe you could let me, hang out with carbon every once in a while. So, I can draw an arrow showing this pair of electrons getting shared with the carbon. Now, carbon doesn't have room for any more electrons right now. Is there a way carbon can make room for electrons? Well, what we can do is have this pi bond move out onto the oxygen to make room for the incoming lone pair. And when we do that, what we get is an alternate resonance structure. And my alternate resonance structure now, one thing I want to point out, none of the atoms have moved. The atoms are all in the exact same spots. All that moved were lone pairs and pi bonds. So none of the atoms have moved, but now, where is the pi bond? Between the carbon and the oxygen. Okay. And if I put in lone pairs on both, originally this oxygen at the top had 2 lone pairs. Now it's going to have 3. Originally this oxygen at the bottom had 2 lone pairs. Now it's going to have 1. And that has formal charge consequences. So what are the formal charges now? Negative on the upper one, positive on the bottom one. All right? So whenever you have a lone pair that's next door to a pi bond, you want to think, okay, there's potentially resonance there. To give another example, let's say I had molecule that look like that. Who's got a lone pair in that molecule? Nitrogen. That lone pair lives next to a pi bond. When I see a lone pair that lives next to a pi bond, I'm going to say, all right, I could imagine that lone pair getting shared with this carbon. Carbon needs to make some space, so carbon pushes the pi bond out onto the other carbon. Then I would draw my alternate resonance structure. Now the pi bonds between nitrogen and carbon. Where's the lone pair? On the carbon. And so that's going to have formal charge consequences. The nitrogen essentially lost an electron in the process because it decided to share its lone pair. So it becomes positive, and the carbon becomes negative. So the first key thing to look for would be lone pair next door to a double or a triple bond. Second thing to look for would be multiple pi bonds next door to each other. So we've already seen one example of that. Looking back, you see an example of multiple pi bonds next door to each other. There's benzene here at the bottom. I have multiple pi bonds nearby. I can push the electrons from one and keep pushing them around in a circle like that. So that's an example where I have multiple pi bonds next door to each other, and I can essentially delocalize them. Another example, hang on. Let me give myself a blank slide so I can. Another example of multiple pi bonds next door to each other. Would be a situation like this. If you have a situation like this where there's two pi bonds next to each other, we can imagine pushing one pi bond over here to this carbon and then pushing electrons out onto oxygen like that. A theme you'll see with a lot of these is we tend to push negative charges out onto oxygen. Why would we do that? Because oxygen's very electronegative. Oxygen likes to pull on electrons. So when given the chance, oxygen likes to pull electrons towards itself. So this is a case where we could draw two resonance structures. And notice all the atoms have to stay in the same places. The sigma bonds are all going to be in the exact same places. The only thing I'm moving are electrons. If you look at two structures and atoms have moved between the two structures, they're not resonance structures. Atoms have to stay in the same place for them to be resonance structures. So where are the electrons now? How is this picture different? Oxygen has 3 lone pairs now. That's going to give it a negative charge. first carbon does not have a lone pair. Right? We took electrons away from it. This first carbon has a positive charge. And the pi bond is now between these two carbons here. So when you have a lone pair next to a pi bond, or you have multiple pi bonds next to each other, those are situations to consider the potential for resonance. So you might ask, all right, why do I have to even consider this? Like, why does resonance even happen? Why is this a thing? Well, I've already kind of hinted at the answer. Electrons like to be shared. All right? When electrons are free to spread out more, number one, remember electrons are traveling in pairs. They're occupying orbitals in pairs, and electrons repel each other. So the more you can allow them to spread out, the happier the electrons will be. And the more nuclei they get to be near, the happier they'll be. All right? So resonance is this situation where you allow electrons to get away from each other and to be close to more nuclei. So you have less repulsion, more attraction. It's a win-win. So resonance stabilizes the molecule as a whole. We use the term resonance stabilized when this happens. So we say such and such a molecule is resonance stabilized. That's a term that we'll use a lot. Yep. So, yeah, so when the electron is shared between multiple nuclei, there's more attraction between the electron and the nuclei. So minimizing repulsion, maximizing attraction, both good things. So whenever resonance is possible, it happens. So it's going to be up to us, when we look at a molecule, to recognize when it's possible, to know that it happens, and then think about what the consequences of that are. Because it can be used to explain so many different things. Other questions? All right. So one thing resonance is going to throw off for us is what we call hybridization. Some of you may or may not have heard of hybridization before. If you've done Module 5, you've done hybridization. If you took Honors Chem, you probably did a hybridization, but some of you may not have talked about hybridization before. But hybridization is just this thing that goes along with electron pair geometry. So it turns out if we consider, let's consider this molecule, this amide that we looked at before. If I asked you 20 minutes ago, what's the hybridization of nitrogen? Think about how you'd respond. Why? The response was sp2. All right, it makes 3 bonds, but it also has a lone pair. All right, how many domains does it have? All right, 4 domains. So we would have said 4 domains. So that would be tetrahedral electron pair geometry, which means not sp2 hybridization, but sp3. So that's what we would say. Without thinking about resonance, we would have said that nitrogen is sp3 hybridized because it has 4 domains, so it has to have tetrahedral electron pair geometry. It's going to have a pyramidal shape. Turns out that's wrong. That's not the observed geometry. So let's go back. Where does that geometry come from? When we have something with 4 domains, we say it's tetrahedral. Why? Why is something with 4 domains tetrahedral? What theory do we base that on? Yep. The VSEPR theory. VSEPR stands for valence shell electron pair repulsion. So VSEPR theory says you take your domains, they repel each other, so you want them to get as far apart as possible. And so if you have 4 domains, tetrahedral is the way to get them as far apart as possible. And that's a very simple idea. It's a very simple theory, right? And it works for most molecules. Just like Lewis structures are simple and they work for most molecules, but they fail when there's resonance. VSEPR theory works for most molecules, but it's not a complex enough theory to work when there's resonance. So it fails when we have resonance. Why does VSEPR theory fail? Well, it's based on the idea that these domains are independent and they just repel and get as far apart as possible. What resonance tells us, though, is that electrons would like to be shared if they can, and the way they're shared is to make those delocalized pi bonds. And in order to make pi bonds, an atom has to have unhybridized p orbitals. A pi bond is made by unhybridized p orbitals overlapping with each other. So, those of you who know about hybridization, if an atom is sp3 hybridized, how many leftover p orbitals are there? Well, the answer is all 3 p orbitals went into the hybridization. None of them were left over. If an atom is sp3 hybridized, it has no leftover p orbitals. So it can only make sigma bonds. It can't make pi bonds. This nitrogen, if it wants to take part in pi bonding, which it does, because when resonance is possible, it's a stabilizing thing. The atoms want to do it. If it wants to do that, it needs to take this lone pair and essentially keep the lone pair in a p orbital that can align with the other p orbitals. All right. So it turns out this is not the observed geometry. What's actually observed is the nitrogen is trigonal planar and it's got sp2 hybridization. It has one leftover p orbital that aligns with the other p orbitals in the pi bond, so that it can make the delocalized pi bond. So I'll go back to that image. This molecule is actually completely planar. See, that nitrogen is definitely not a pyramid. It's perfectly flat. And the reason it's perfectly flat is it needs to have p orbital lined up with the other p orbitals to make this pi bond that looks like a boomerang-shaped hamburger bun. So resonance, when there's resonance, not only is one Lewis structure not good enough, Lewis structures aren't good enough, VSEPR's not good enough. So when figuring out hybridization for situations where there's resonance, you have to imagine that the lone pair no longer counts as a domain, because the lone pair is no longer really alone. The lone pair is being shared. All right? So it turns out that this is wrong. So let's talk about the right way to think about it. So the right way to think about it is to consider the resonance structures. So we've already drawn it once, I'll draw it again. Here's my structure. I can imagine this lone pair being shared with carbon and this pi bond being pushed onto oxygen. And what this tells me is this lone pair is not really a lone pair. You know, and I can actually draw it in purple up here because it's still the same lone pair here. You know, still we can imagine it being the same pair of electrons. The purple lone pair is not really alone. And because of that, if we're thinking about the number of domains on the nitrogen, it really only has 3 domains. We don't count that lone pair as being a separate domain because it's going to be part of the pi bonding. We call it the pi system. Okay? So it does not count as a separate domain. So what we would say is the nitrogen actually only has 3 domains. So it would be trigonal planar, and it will be sp2 hybridized. So just to quickly summarize, resonance is a failure of Lewis structures. It means a single Lewis structure is just not good enough. The actual structure is a hybrid of resonance structures. Forgot the S there. Molecules with resonance exhibit delocalized pi bonding, pi bonds that are shared among more than 2 atoms. The actual structure resembles the more stable resonance structure more closely, if one is more stable than the other. Resonance stabilizes the molecule as a whole, and resonance changes the hybridization we would normally expect. So, important concepts. We will revisit these all the time once you get past Module 6.